dynamics, particularly within LRC circuits, and I want to focus on phase in this conversation. Now, phase sometimes feels a little mysterious, but it actually is fairly reasonable, and there's a lot you can learn by seeing the phase. In fact, understanding the phase plot or the magnitude plot are really very similar things, and you can almost get one from the other, it turns out, in theory. So it's really important to see what does it tell you, because it'll often help you as you're proceeding forward. So I want to look at this in terms of three circuits: a low-pass filter, a bandpass filter, and a high-pass filter. Now, the nice thing about this is that it's actually, these are slightly different circuits than maybe the classical simple canonical form, but there's so many different permutations that still give you a nice second-order dynamic. So all three of these are a little different, but they're actually not that hard to see what's going on. One is I've got an inductor with an R and a C, and this is basically a voltage divider. You might say, why is it a voltage divider? Well, again, remember my capacitance is something that's 1 over SC. My inductance is just S times L, and these are in Laplace domain. It's wonderful when you get to deal with circuits in Laplace because your L's and C's can all basically just turn into resistors. And you can do a whole different permutation, but we'll just start with that, okay? And so this gives me one case of an R and a C in parallel with the L. So this would then give me a parallel combination of RC and then the SL, and that gives me this sort of typical voltage divider expression. Here the L and the C are in parallel, and then I would add the R, so it gives me the L and C in parallel plus the R. And here I get the L and R in parallel plus the C, the R and L in parallel plus the C. This gives me now three straight formulations, a little bit of math, and I end up noticing I get a 1 over 1 plus SLR plus S squared LC. I get a same denominator in the bottom case, but I get an S times LR in the numerator here, and I get an S squared LC in the numerator here. Quite useful because all of these kind of fit together. These all then fit into canonical forms of where I can talk about what is my tau and what is my Q. And so then I would ask, well, what is my tau, which is LC? And if I take a look at LC, which is tau squared, just use two values, 200 millihenries and 125 picofarads. That gives me a time constant of 0.16 milliseconds, or a corner frequency that's basically 1 kilohertz, which is really nice for plotting. Yes, I did choose some values so I could actually work with it. Keep the math really simple. One of the other things that's very important for any of these cases is this value of square root of L over C. And square root of L over C is actually units of resistance. Quite useful. You'll see this in lots of different cable and other electromagnetic stuff. Useful a lot of places. But we'll start with that. And it turns out for this value it's going to be 1.25 kiloohms. And so what's interesting is that Q is going to be R divided by this quantity. So I'm going to be looking at different values as I build up for this. So if I wanted to look for a Q of 1, I would have a resistor that's going to be 1.25 K. If I wanted to have a Q that was say 1/8 or 0.125, it would be about 156 ohms. If I wanted something that's a Q of 8, it's going to be 10 kiloohms. And I'm going to be looking at a group of 7 values here that I can then plot and take a look at the phase behavior. So that gives us something to kind of think about here. Now, when I'm at Qs that are less than a half, remember half is kind of a critical number, or a half is a critical number, I've got real roots. Now, at half, they're identical. Below half, they're going to be 2 different roots. And one of the things you see in all 3 of the phase plots, and by the way, notice all 3 of the phase plots look almost identical. Not surprising because the numerator is going to drive the discussion, and what happens in the denominator is either going to give me a 1 or a J. J is going to then shift me by 90 degrees, or a J squared, which is then going to give me 180 degrees or a -1. So there's no shock that all 3 of these curves look basically the same, except that notice for the first one it goes from 0 to -180. The next one goes from 90 to -90, and the third one goes from 180 to 0. So basically, this is not a surprise that we're getting 3 curves that look identical. So how do I then think about it for different Qs? Well, the Q equals to 1/8, I know I'm going to be having different roots, which means that I'm going to be looking at things that are going to going to almost try to get all the way down to 90 degrees. I'm going to get about 45 degrees of phase shift. It looks like I'm getting almost this sort of tangent-like curve there. And then it's going to try to get to 90, but doesn't quite. And kind of interpolates out to the second one, which is sitting about here and curls all the way down. So that's where I'm going to see the Q equals to 1/8. I expect it's going to be dropping down. And by the way, I can look at this when the angle would have been 45 degrees and go, what's the value at 45, how far off in frequency? Well, that's going to basically be about a factor of 8 here from that center. You're going, and if I look at similar sort of thing, about 8 from that center, and you're thinking, that's exactly what I would expect. If I look at it for 4, it's going to be about a factor of 4 from the center, so it's about 0.25. And in fact, yes, that's what I see there, about exactly where I would see it there as well. And so I can, at Q equal to 1/2 is the double roots. And so it has a very smooth, almost perfectly smooth trajectory. When I start going to higher Qs, this gets to be higher and higher and higher gain. And so what I'm going to see is that it keeps going in height. It looks like it's going to be flat here. So 1/2 is that special case where it looks like a double root, so nothing is moving. So what do I get higher gain from that? I get 1, 2, 4, and 8 gets rather steep here. In fact, notice how fast this shifts from 8 from the top to the bottom curve. So it's really neat to see what you can get in terms of the phase curves. There's a lot that you see out of this, even though a lot of times people are like, phase is a little bit scary. It's really not, and it actually gives you additional information that really helps understand these physical systems and what you're building.